Thank you very much, Hans, and everybody, for giving me the opportunity to speak about the Arqiva DAB network. Before we get into the way in which Arqiva has designed and built this network for long-term operational performance and how we use synchronization, I thought it would be good just to brush up and have a quick look at some of the basic principles of why we need synchronization in DAB. So please, next slide, Michelle. Okay, so DAB uses wideband OFDM technology where we have 1536 carriers, and we basically modulate the carriers with 2 bits per carrier per symbol period. What this basically means is that the signal is extremely robust. If you could press the down button, please, Michelle. This means that in both a Gaussian channel, which is basically a condition where we have a good line of sight condition between the transmit antenna and the receive antenna, which is on the left-hand side, we've got a nice shaped OFDM receive signal. It also works very well in much more normal conditions, especially for mobile reception. For example, a car, where you might have local reflections, where we have an outcome where we might have some fading into the channel, which is the right-hand diagram that you see. But it means that it's very robust because we basically modulate a small amount of information across a large number of carriers. In addition to the DAB signal being very, very robust, it also exhibits a very good spectrum efficiency. So on the map on the right-hand side in the UK is an example of one of the UK national DAB licenses, where you can see there are many transmitters in a single network, well over 400 in the BBC DAB network in the UK. And importantly, all of these transmitters work on the same frequency. But to work on the same frequency, we need to adhere to some pretty strict limits. If we don't adhere to frequency synchronization, and at 200 megahertz, we need about 0.1 parts per million, which is about plus or minus 10 hertz of frequency synchronization, that can lead to inter-carrier interference. But also we need to time the network so that we transmit those signals, those symbols, from each of the transmitters at the same time. Because if we don't time the network, that can lead to inter-symbol interference. And if the timing of the network isn't carefully controlled, we can really degrade the performance of the SFM. Next slide, please. So in this scenario then, we've just basically said that we need to time the network so that all the transmitters transmit the same symbols into the SFN at the same time. But even with this scenario here, where the receiver is in this car, in the real world, what's happening, of course, is that it's very unlikely, or many times when that receiver is trying to decode that DAB signal, it isn't just going to be having a direct line of sight path. Often what happens is that signal is subject to multipath, which basically means that we're going to have echoes of that transmitter, or of that service, being received by at the receiver, which basically means that we've got multiple versions of the symbol. What makes it even worse, if you press the down key, please, Michelle, is that we could have a second transmitter in our SFN with a different propagation delay being received at the receiver. So how does the receiver cope with this condition where you've got multiple versions of the same symbol being received? Well, if you could press the down arrow again, please, Michelle. Here, what we do is that we actually extend the active symbol period by a period known as the guard interval, and this allows the receiver to actually do the 1 millisecond integration time. So that avoids inter-symbol interference. Next slide, please. So we've said now that we need to transmit the same symbols from the transmitter at the same time. Basically, how do we do that at a very high level? Well, we timestamp at the ensemble multiplexer at the head end, and that timestamp value ensures that the baseband frame is released to the channel coder in the DAB transmitter at exactly the right point with reference to 1 pulse per second. But what we also do is that we offset that timestamp to allow for the propagation delay through the network. And as we've shown on this diagram, there could be a number of different propagation delays to that network. So the combination of the timestamp offset and basically reference to one pulse per second allows us to transmit the same or process the same baseband frame and the same symbols into the SFN at the same time. In addition to that, at the bottom of the screen, you see that we also have an adjustable delay as well. This enables us to put different types of manufacturers' equipment into the network to ensure that we can co-time all of our transmissions, and we can also use this to trim the time of which we release the baseband frames into the channel coders to optimize SFM reception. And on the right-hand side, you can see a 96 millisecond transmission frame with the 77 symbols, and we basically need those frames to be radiated at the same time into the SFN. Next slide, please. So this is very much a simplified network drawing of the Arqiva DAB platform. You can see, if you look at the bottom of the slide, it's a combination of packet-based interfaces and also frame-based interfaces. Fundamentally, of course, the whole network needs to be synchronized, like we said, but the precision of synchronization is different at different elements of the design. For the audio encoder and the audio decoder, we use NTP. For the audio encoder, we insert timestamps into the RTP headers, and this allows the audio decoder, which operates in parallel pairs, to time align the output of the audio decoders. And the golden rule here is that we need to make sure that the outputs are aligned to within about 20 milliseconds. Otherwise, if we switch between those two outputs, the listener is likely to hear a jump in audio. But because we can achieve a precision of about 10 milliseconds accuracy over NTP, that allows us to use NTP to generate timestamps and to provide that alignment. On the audio decoder, we also use it for sample rate conversion, which allows us to maintain on average the correct number of samples at the input to the multiplexer. On the multiplexer itself, again, we use NTP because we use a deterministic frame count 0. And in our deterministic approach, what we do is that when the ensemble multiplexer is initiated, it effectively counts back from an epoch period so that we know that we have the correct value of the timestamp with its timestamp offset in frame count 0. Now, that doesn't have to be exactly accurate with respect to 1 pulse per second on the output of the multiplexer. So we just need that into round about the right point. So that allows us also again to use NTP, and an accuracy of about 10 milliseconds is good enough for that application. On the output of the multiplexer, we send EDI over a wide area network using multicast. And at the edge of our WAN, we have a large number of EDI to ETI converters. And at this point, the precision of our reference becomes much more important, because here we need to very accurately and very carefully clock out the baseband E1 frames. So on the bottom of the diagram, you'll now see that we've got 10 megahertz as our principal clocking reference to control the numerically controlled oscillator on-side that EDI to ETI converter. And this ensures that we manage and we maintain a maximum rate of change of what's known as the frame phase to about 1 microsecond. 1 microsecond per second as worst case into our E1 distribution network, which is generally speaking SHF distribution networks or indeed over satellite. But to ensure that we don't compromise that maximum rate of change of frame phase for the ETI frames, we actually use SyncE to ensure that we successfully deliver those ETI frames across this wide area network. And of course, at the DAB transmitter, we use 10 megahertz to maintain the frequency of the transmitter, and we use 1 pulse per second to make sure that we're processing those baseband ETI frames into the transmitter channel coder at the right point with respect to 1 pulse per second. On the left-hand side, you'll also notice that the NTP derived for the or by the NTP clients, I should say, sorry, on the audio encoders, decoders, and multiplexers are all classically driven by a distributed NTP design. What this basically means is that we have carrier-grade GNSS receivers in the core of our network, and that enables the clients to subscribe to up to 4 diverse NTP sources, which enables us to remove any false tickers. So in other words, if one of those GNSS receivers becomes unstable. But because we only need 10 milliseconds accuracy at the NTP clients on those 3 devices, we're able to use a classic NTP distribution design. However, what we found throughout our type approval process is that on the EDI to ETI converters, we really wanted a second interface because of the crucial part they play in the distribution from the multiplexer to the transmitter network. We wanted a second clocking interface into the EDI decoder. So we worked very hard with one of our manufacturers to develop a conditioning algorithm based on NTP. But here we needed to basically break some of the traditional rules. So here our EDI decoders, the NTP clients on those devices directly tunnel all the way back through to the core NTP servers to improve the precision and the accuracy of our reference, which we derive from the NTP polling, which comes from the client on that EDI converter. What we also do is that on each of our GNSS receivers, they're multi-constellation designs. So that enables the GNSS receiver to constantly compare between the different constellations. And the aim of that is to determine that if one of the constellations becomes unusable, we're able to remove that from the pool, and we can then continue to operate with the same equipment, but we're not using one of the constellations which might degrade the quality of the synchronization on our network. Can you press the down button, please, Michelle? Keep going, sorry. Keep going, keep going, keep going. And one more. Okay, thank you. So just to give you an idea of the scale, obviously this is just a high level simplified diagram, but this network is very large. The actual scale of it is that we actually have 430 unique audio services. So those audio encoders are hardware codecs, which we have at a very large number of studio sites. Because we use those to send multicast traffic into our head-end system, we're actually using those 430 audio services for 700 audio services on the DAB platform, and our transmitter networks for just the commercial radio networks in the UK are 745 transmitters. So when we include the BBC network, where we are doing the ETI distribution and the transmission element only, we're operating over 1,000 transmitters in the UK. Okay, next slide, please. Okay, so it's quite clear then, I think, that we obviously use GNSS extensively to synchronize and time the Arqiva DAB network in the UK. But it's probably worth just thinking about some of the issues that we've experienced on GNSS over the years. Some of them are much more difficult to manage and mitigate, and some of them are perhaps about installation as well. So the first one really is about obscuration. Here, really, this is perhaps going to affect sites where you're in dense urban environments, or maybe rural areas where you're surrounded by lots of trees. This is all about the GPS antenna having a good view of the horizon, because you need a certain number of minimum satellites that the receiver can see before the receiver will work accurately for you. So obscuration's often about trying to make sure your antenna has a good view of the horizon. Then we've got interference jamming and spoofing. So often interference is non-intentional. We've suffered this sometimes on some of our main broadcasting sites where we have very high power UHF co-sited, and often we've found that we have harmonic issues coming from the UHF services, but because of the VRP of the transmit antenna, we're able to physically move the antenna around the site to reduce the level of the harmonic falling on the receive frequency of the GNSS receiver. Jamming, this is obviously a bit more difficult to control. In the UK, we often call this the white van effect, where there's very much local jamming, which is possible from wideband noise, low-level noise, which is being generated by jammers in white vans, quite literally. But because the GPS and the GNS signals are so low, around about minus 130 dBm, just low power jammers can cause you problems. But often we find in the UK that the jamming issues are short term. One mitigation effect that or one mitigation approach that we found quite useful here is the use of good SAW filters. But then you need so we improve the selectivity of the receiver. But here you need to be careful about group delay. So it's a compromise between what you do for trying to remove and trying to mitigate against jamming. We also recognise in other territories that jamming can be much more widespread, but for the UK at the moment, it seems to be much more of a local issue that we need to manage. Then, of course, there's spoofing. This is a condition where this is much more subtle. So the receiver still thinks that the incoming GNSS service is good, but it's purposely being changed. And this means that the receiver will continue to operate. In fact, it might not even give you any alarms that it is being spoofed because it doesn't know it's being spoofed. And this is possibly a really difficult and quite involved problem to manage and to mitigate. And the one way that we found, or we thought about doing this, is to use multi-constellation GNSS receivers, which is across our entire network. The next issue could be space weather. So here we have solar issues which change the ionosphere, and this can effectively change the path conditions between the satellite and the receiver. Yeah, this is quite a difficult thing, and here what we find is that we use GNSS receivers with oscillators with good holdover characteristics. And then finally, of course, there's configuration issues. So even though these platforms are often state-owned and well managed, even they can have problems in the configuration of their GNSS platforms. There was quite a famous event in 2016 when the US government was changing or actually decommissioning one of the satellites, and the process went wrong, and the satellite continued to operate, but actually it was 30 microseconds off when compared to 1 pulse per second, which did cause some problems to DAB networks. So it's clear then that GNSS, the resilience element of GNSS, needs to be pretty high in your network design and network planning because of the reliance that we have on those platforms. Next slide, please. So I'm just going to show very quickly now 2 quick case studies about what happens perhaps when timing goes wrong in your network. So this first case study really is about as simple as it gets. It's just 2 transmitters. This is very much a simulated network. So others from the UK will see that I've configured my bench network to have 2 sites called Crystal Palace and Rutham. These aren't the actual Crystal Palace and Rutham. This is just a bench scenario. So we're going to play a short video in a moment, and within the video, what you'll notice is that we start with a specifically configured offset of about 50 microseconds between Crystal Palace and Rutham. And on the top right-hand side of the video, you'll see the channel impulse response with 2 spikes. And after probably about 10 seconds or so, I specifically reconfigure one of the transmitters to be at the edge of the guard interval. And then finally, at the end of this video clip, I reconfigure the transmitter to be well outside the guard interval. Now, of course, reconfiguring is the process that I've used to demonstrate this in this video, but it's the same effect, although not coming and going at specific time intervals, but a transmitter, one of the transmitters in the SFN, slowly being mistimed because it's lost its GNSS reference. On the left-hand side is a spectrum planning map, which shows the first configuration. So the red dot on the map is the receiver, which is roughly equidistant between the two transmission sites. The transmission sites are shown by the two black crosses. So if you, Michelle, could now press the down arrow. Don't think we can hear the audio. I can't. Okay, I think, Michelle, we can't hear the audio, so not to worry. Okay, the point is that the what the video would have shown you is that as you progress the timing offset between the transmitters from being 50 microseconds to on the edge of the guard interval, the receiver works well, and then when you go beyond the edge of the guard interval, the receiver starts to fail. And on the bottom map, what you can see is the outcome when two transmitters, or one of the transmitters, sorry, is configured to operate outside of the guard interval. You might think in the bottom map that there would be a much more pronounced area of loss of coverage, but this is because of terrain shielding, because the predictions were done using a actual spectrum planning model. Okay, page down, please, slide down. Okay, so the second scenario then is all about what happens if GNSS generally becomes unusable to us. GNSS is a number of different constellations, of course, generally owned by state providers. So as network operators, we've probably got little control in certain times. So we need to think about what actually happens if GNSS becomes completely unusable to us. So on the left-hand side is a very much simplified transmitter design, very, very simple. And basically what we would classically expect is to have a frequency processing module, which would have an onboard GNSS receiver. We might also be able to have external 1 pulse per second and 10 megs to drive that frequency processing module. But if the external 10 megs and 1 pulse per second becomes unusable, plus the GNSS is not available, we would then go on to the internal oscillator inside the frequency processing module. At that point, we enter a period known as holdover. So within our designs, what we also strive to have is natively good holdover characteristics of the oscillator. We found that double oven controlled oscillators, double oven controlled oscillators provide us with about 50 microseconds drift over about 5 to 7 days. And that enables us to manage the effects when GNSS is lost in our SFN. Importantly, though, at the end of this period, we also need the ability to mute some transmitters as well if we're unable to return to GNSS as a reference for our network. Okay, slide down, please. So how do we monitor synchronization in our network? So we've talked a lot now about how important it is. So we monitor how we synchronize and the condition of our synchronization at many different places across the network. On number one, as you see through the diagram, we actually have the ongoing monitoring of the NTP service on our NTP clients. So on our NTP clients, we're doing two things here. We're looking at the individual connections to each of the NTP servers. So here we can look at long-term statistics to look at jitter and packet loss and so forth, because our conditioning algorithms are able to avoid using some highly jittered or lost packets without changing the clocking output of the actual the conditioning algorithm. The second thing is that the NTP clients are also looking for false tickers. So if one of those GNSS receivers becomes unusable, the client is able to remove them from the pool. Moving along the diagram to where it shows number 2, here this is much more crude. This is just looking at the 10 megahertz reference provided by the co-sited GNSS receivers to the EDI decoders. This is looking for a compliant 10 megahertz electrical interface, and should that fail, then the EDI converter will revert back temporarily to the NTP derived clock. The number 3 on the diagram, which applies to all of our GNSS receivers, is the ability for these to all use constantly and compare between more than one constellation. So these are all multi-constellation devices. So they're constantly measuring and trying to compare and make sure that if one of the constellations becomes unusable, that again, it's removed from the process. Number 4 on this diagram is an in-house piece of equipment that we've used for many years, and we call this the transmitter timing module. The transmitter timing module sits in each of our transmitter bays, and they all have their own GNSS receiver generating 1 pulse per second. And there's a fixed relationship between ETI frame 0 and a 96 millisecond transmission frame every 12 seconds. So for each transmitter, there is a fixed offset between the 1 pulse per second and when the occurrence every 12 seconds of those 2 frames. And under normal conditions, that offset doesn't change. However, if the transmitter becomes or loses its synchronization, then that offset will start to drift, and at that point it signals that condition to our operation center, and we know that that transmitter has now become or the synchronization, if you like, or the timing reference to that transmitter has become untrustworthy. And then finally, we also measure constantly transmitter storage times. So storage times will be constantly changing by a small amount because of path variation into the transmitter, but we don't expect large leaps. So we have windows where we make sure that the transmitter doesn't exceed a set value to make sure that the transmitter stays within a certain window of operation. Okay, next slide, please. So in addition then to having constant monitoring, which is all connected to our broadcast operations center, it's also important to have tools that you're able to deploy when there might be listener complaints, or indeed to validate when there's major network changes. So in the two diagrams at the bottom of the slide is a recent use case of some of our mobile measurement equipment looking at time and synchronization of the network. We've recently migrated some of our DAB muxes, and effectively we wanted to look a before and after timing characteristic of the network because we should see no change. On the left-hand side is a map of one of the multiplexes in the Northamptonshire area, and the red dot with a black circle around it is a location which we selected because the key on the bottom right will show you that in this regional DAB network, if you went to that location, we could see all 6 transmitters from the SFM. And on the top right of our test equipment, you can see that we can see all transmitters. And we know the relative timing of the transmitters in the SFN at that location, and therefore we could easily do a before and after approach where we looked at the relative timing of those transmitters in the network before and after the migration. Okay, next slide, please. So this is just more of a conceptual thing. Of course, we've not really stopped thinking about synchronization inside Arqiva, and we are starting to think about what our next steps might be. So the first thought that we are thinking about now and we're working through is the ability to use PTP. So all of our GNSS receivers are already PTP aware. The servers, which are effectively in the core of our network, these are already able to serve PTP to the network, and our GNSS receivers deployed around the edge are already classed as PTP boundary clocks. However, the sometimes quite complicated part is actually to generate or to build a PTP aware IP distribution network. So this perhaps in some cases can be cost prohibitive. So we're looking at the ability to do PTP, but this is work in progress. The next step perhaps would be to add a cesium clock. Cesium clocks are fantastic because you're able to condition a cesium clock, but if that conditioning interface is removed, they have excellent holdover characteristics of perhaps less than 1 microsecond drift over a year. So in principle, you could use a cesium clock to condition the whole network, then the whole network effectively drifts together. And that means that you can continue for very long periods without the requirement for any external conditioning into your network. The downside, of course, is that cesium clocks can be extremely expensive, but it's definitely another thought. And then our final thought is about terrestrial synchronization of the network. In the UK, there is some discussions of terrestrial platforms being developed, such as ELARAN. Should this be developed as a platform, which is obviously outside of Arqiva, this is a kind of state level investment, then we would definitely be considering the use of ELARAN to perhaps synchronize the network as an additional interface and complementary to GNSS. Okay, slide down, please. So in the conclusions then, it's clear that synchronization for the DAB networks is absolutely essential. And it's certainly the case at the moment in the UK that we rely on GNSS to provide that synchronization. We also think that there can be some relatively, not straightforward, but relatively low cost mitigation techniques such as multi-constellation GNSS receivers and oscillators can be deployed in transmitters with good holdover characteristics to improve resilience should the GNSS platforms become unreliable. Other techniques are definitely being thought about, but in some cases they can be a little bit cost prohibitive, but nonetheless we need to continually evaluate the resilience of our network. And it's also very important to make sure that you continuously monitor the configuration and operation of your network and also provide the ability to do mobile measurements when necessary. And that's it for me. Thank you very much.